Thanks to Brilliant for sponsoring today's video.
Today I'd like to see if we can weave our way into some sort of algebraic structure where it makes sense to divide by zero. So let's start by looking at why you can't really do this in the normal rational numbers. And then we'll build some sort of like version of the rational numbers, or really it's an extension of the rational numbers where this sort of makes sense. Okay, so let's maybe recall how the rational numbers are fundamentally defined as equivalence classes of ordered pairs of integers cross natural numbers. You know, modulo an equivalence relation. So we did this on the channel before. You should check out that video if you'd like to. So the equivalence relation goes like this. So a comma b is equivalent to c comma d if and only if ad equals bc. And here we would write the fraction a over b is given by the equivalence class a comma b. And notice that this equivalence relation here is really just, giving us the ability to simplify fractions down to lowest terms. So let's notice that 2 over 4 is the same thing as 1/2. But note that the ordered pair 1/2 or 1 comma 2 is equivalent to the ordered pair 2 comma 4, and that's because 4 is equal to 2 times 2, and that's just using that equivalence relation that's just above. Furthermore, let's notice that in this setup, we don't allow division by zero because here we're taking the natural numbers not to contain zero. And so that means the denominator will never include a zero here. Okay, so the big question here is, can we extend this so that division by zero is allowed? And so let's look at the standard attempt to do this and see where this goes wrong. And then let's see if we can do something a little bit more careful. Okay, so the standard attempt would be to define this thing called q hat, which is equal to all of the rational numbers q union something that we'll call infinity. And infinity satisfies a couple of the following rules. So if we take a non-zero rational number, which I'll call a, up here a is an integer, but here it's going to be a rational number. I think that's okay. We have a over 0 is equal to infinity. And so notice this includes like positive and negative rational numbers. So if you go infinitely in the positive direction or infinitely in the negative direction, you still like go towards infinity, if you will. So in a sense, this is like taking all of the rational numbers and then wrapping them up into some sort of circle. So at the top, we've got infinity, and the bottom, we've got 0. And you might say, well, why aren't we doing this with the real numbers? And in fact, we could just as easily do this with the real numbers. And this is some extension of the real numbers, which is topologically equivalent to a circle. That being said, for the, more algebraically proper extension that we're about to look at, I think it's nice to look at the rational numbers only. Okay, well, in this setup, generally, we take things like this as well. So we would have a times infinity to be equal to infinity. And this is for non-zero a. And then we would also have a plus infinity to be infinity. And I guess like we would also put infinity plus infinity is infinity. But under this setup, there are still some things that are undefined. And some of those things that are undefined are 0 over 0. So we would take that to be something undefined under this extension. 0 times infinity, and then also infinity over infinity. So those are all undefined in this setup. And all of these things are in fact undefined because if these were defined, you would end up with some pretty big problems. So if you were to take the number 1 and write it as 1 over 0 times 0 over 1, which seems reasonable. I know I just said that these were undefined. I guess I said it out loud, but I didn't write it down. So undefined here. Then, well, if you don't take these to be undefined, well, this would be some sort of reasonable expectation. But let's observe that this brings about a problem really quickly. So observe that this is 1 over 0 times 0 plus 0. Well, because the second term is simply 0, and 0 plus 0 is 0. But observe that distributing that through, you get this. This is 1 plus 1, which is equal to 2. So here we have 1 is equal to 2. And in fact, you can do some similar calculations to show that every rational number is equal to every other rational number. And, well, what's going on here? Well, this is in fact why this extension of the rational numbers leaves these objects right here undefined. And our whole goal today is to look for some sort of structure where nothing is undefined. So it would be allowed to divide 0 by 0. It would be allowed to multiply 0 by infinity, and it would be allowed to divide infinity by infinity. Okay, so let's see how we might do that.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. With Brilliant, learning isn't just a task, it's an adventure. Dive into thought-provoking courses designed to challenge and inspire, covering topics ranging from mathematics and computer science. Dive into thought-provoking courses designed to challenge and inspire, covering topics from mathematics and science to computer science and beyond. Brilliant's enormous library of learning content allows active learners like you to explore a variety of topics and skill levels, and Brilliant will support you every step of the way. Whether you're a student striving for academic excellence or a lifelong learner hungry for new insights, Brilliant has something for you. Engage with interactive lessons, solve stimulating problems, and watch as your understanding deepens and your skills soar. You will be able to master whole topics gradually in as little as 15 minutes per day by sharpening your problem-solving skills. I recently started exploring their growing number of programming courses. It's a great way to learn how to use Python. There are no boring lectures here. You will learn with their hands-on approach. Give it a try and see how much fun it is. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial and 20% off your annual premium subscription. Thanks once again to Brilliant for sponsoring today's video.
So in order to properly extend the rational numbers to have this division by 0, we actually have to go back a couple of steps. We can't just start with the rational numbers as z cross the natural numbers and that normal equivalence relation. That is essentially cross-multiplying fractions. What we have to do is, well, start with z cross z and a new equivalence relation. And I'm not going to exactly go into that equivalence relation and the equivalence classes and stuff. I'm just going to write it kind of in the conclusion. And the conclusion would end up with the following type of structure. So I'll call this Q sub W, and that's because in general, this type of algebraic structure is called a wheel, and we'll define that properly at the end of the video. Okay, so this is everything of the form A by B or A over B, but notice I'm not writing it as a fraction as I did before. I'm doing this kind of slanty fraction just to make it look different than the normal rational numbers that we had before. And this is A and B are integers. That means you could also include 0 in the denominator. And then we have A by B is the same thing as C by D, if and only if there are non-zero integers x and y, where ax equals cy and bx equals dy. So notice that our, rule for equivalence of fractions, if you will, is a little bit different here. It's not just the cross multiplication rule. Okay, so let's see what we get out of this setup. So the first thing to notice is that we have normal, what I'll call normal fraction equality here. And what I mean by normal fraction equality is as long as there's no zero in the denominator, fractions are equal exactly the same way they would be in the normal rational numbers. So let's maybe assume that in this setup, we have b and d are both non-zero. And let's see that a over b is equal to c over d if and only if we have AD equals BC. And let's maybe go in the language of this over here. So in the language of this equivalence relation, what we would do is we would set x equal to d and we would set y equal to b. So note that our AX equals CY equation in this setup would turn exactly into our AD equals BC equation. And then our BX equals DY equation, well, that's actually pretty boring here. That immediately just turns into BD equals BD. But needless to say, the important thing here is that if you don't have a zero in the denominator, then our new fractions are equivalent exactly the same time our old fractions were equivalent. Okay, well, let's see some other properties of this structure. So let's notice if you have a zero in the denominator, then everything is equivalent to 1 over 0. Well, that's assuming that the numerator is not 0. So let's maybe note the following. So if we have a not equal to 0, then we have a over 0, or I should say a by 0 is the same thing as 1 by 0. And well, let's see why this is. So let's try to set up our system of equations over here for x and y. So that means I would need a times x equal to 1 times y, because that's our rule for the so-called numerators. And then we would need, let's see, 0 times x to be equal to 0 times y. But observe that this thing holds all of the time. That's because, that's just within the integers there. That's 0 equals 0. So now let's observe that since a is not equal to 0 by our assumption in this case, and x and y are not 0 by our assumption inside of the equivalence relation, that means that we can simply take perhaps x to be equal to 1, and we could take y to be equal to a. So if we take x equal to 1, y equal to a, then that solves this setup right here and, well, gives us the fact that these two fractions are equal. So anything over 0, provided that your numerator is non-zero, is the same thing as 1 over 0. So I guess that motivates something over here, and that's the introduction of a new number here, and we'll just call this infinity. So we'll take 1 over 0 here, and we'll just define that to be equal to the symbol infinity. And I think this is pretty reasonable because whenever you've got a 0 in the denominator and non-zero in the numerator, well, what you have here is the same thing, and we might as well call that just one thing. And then maybe the last thing to notice here is that 0 over 0 is a brand new element. So 0 over 0 is I'll call it new element. In other words, it's not equivalent to anything else, unlike these other cases up here. Here we've got normal fraction equivalence. Here we've got lots of different ways of writing infinity. But here, 0 over 0 is totally brand new. And let's see why that's the case. So let's take a over b and say it's equal to 0 over 0 and see what it would take for something else to be equivalent to 0. So that means you would need x and y, both non-zero, making this happen. So in other words, you would have ax equals 0, and you would have, or 0 times y, I should say, and you would have bx also equal to 0 times y. But notice 0 times y in both of those cases is equal to 0. Oh, but observe that we assumed that x was non-zero. So since we assumed that x was non-zero, and we have ax equals 0 and bx equals 0, then that quickly implies that a and b are 0. So in fact, we have, well, our original thing there, which was just 0 over 0. So that's our brand new element that's not equivalent to anything else. And let's give that a name as well. And we'll call that perp. Or yeah, we'll call it that right there. So that symbol, so this is going to be defined to be our 0 over 0. Okay, so let's see what sort of arithmetic we get out of this. Okay, so let's just recall the types of elements we have in this new structure. Well, they're numbers that look like normal rational numbers. So in other words, the denominator is non-zero. We've got this infinite element, which is 1 over 0, and we've got this like perpendicular element, which is 0 over 0. And now let's see if we can define addition and multiplication the same way that we would in the rational numbers. And we'll see that we will be able to make this definition, and almost everything works. It's just we have to tweak some of the rules that are satisfied here. Okay, so let's note that we've got this normal thing, this AD plus BC over BD here is coming from maybe finding a common denominator. And here, this is just like multiplying straight across the fraction. Okay, so let's maybe look at some sample calculations. So, well, it'd be nice to know what something plus infinity is. So let's look at that. Let's do it in terms of 1 plus infinity. Although you could really do this in terms of any rational number plus infinity to get an idea of what's going on here. This is just a worthwhile example which serves as like a representation of what's going on. Okay, so anyway, that's going to be 1 over 1 plus 1 over 0. But then using this rule right here, that's going to be 1 times 0 plus 1 times 1 over 1 times 0, which is clearly 1 over 0, which is infinity. So we've got 1 plus infinity equals infinity. And I think it's pretty easy to check that from this it follows that as long as you've got one of these finite rational numbers, so in other words, something that's not like this or not like this, so it's our kind of familiar type, then you get that plus infinity is equal to infinity. So if we have a over b, b is not equal to 0, then a over b plus infinity is equal to infinity. And you can do the calculation in general, but it's essentially the same thing as what's going on right here. Now, what about adding something to the perpendicular element? So, well, let's add 1 to the perpendicular element just as a representation of what's going on, and then you'll see that something general happens over there. So we've got 1 plus perp. So that's going to be 1 over 1 plus 0 over 0. But then using our addition rule up here, that's going to be 1 times 0 plus 1 times 0 over 0 times 1 again. Oh, but then let's observe that this is simply 0 over 0, which is perp again. So this is like another type of infinity almost. Note that here we've got 1 plus that is equal to, well, itself. And, you know, this is like going to be extended to all non-infinite rational numbers as well. So if you take a over b with b not equal to 0, then a by b plus perp is equal to, well, again, the perpendicular element. Now, well, you might say, well, those two boxes don't cover the cases when we add infinity to infinity, perpendicular to infinity, or perpendicular to perpendicular. So let's look at those. So let's look at first infinity plus infinity. So that's going to be 1 over 0 plus 1 over 0. Oh, but let's observe that that is equal to 1 times 0 plus 1 times 0 over 0 times 0. In other words, it's 0 over 0, which is the perpendicular element. So there we get something that's a little bit less expected, I would say. And then maybe like similarly, and I'll leave these as little homework exercises, you'll find that if you take infinity plus the perpendicular element, you get the perpendicular element. And if you take the perpendicular element plus the perpendicular element, you get the perpendicular element. So in fact, that gives you a complete, set of rules for adding these numbers from this extended rational number wheel, if you will. So you add them like normal if you've got non-infinite elements, and then, well, all of these rules help you otherwise. Okay, so now let's see what we get out of this multiplication rule. Okay, so let's see what we get out of this multiplication rule now. Let's first take a and b not to be equal to 0, and we'll see what happens if we multiply finite non-zero rational numbers into infinity and the perpendicular element. So let's observe that a by b times infinity, well, that's going to be a by b times 1 over 0, but that's going to be a over 0, just because it's a times 1 over b times 0. But then we're assuming that a is non-zero here, so we do get infinity. So maybe we could see this. A over b times infinity is equal to infinity. And then, well, let's maybe do a over b times the perpendicular element. So that's a over b times 0 over 0. But that's going to turn into 0 over 0, which is our perpendicular element again. But now let's notice this. Let's notice if we take infinity times infinity, then we'll have 1 over 0 times 1 over 0, which is, again, another 1 over 0. But that's going to be infinity, so that's how you would multiply two infinities. If you take infinity times 0, well, then we could write that as 1 over 0 times 0 over 1, which by our multiplication rule is 0 over 0, which gives us our perpendicular element. Furthermore, this a over b times perpendicular gives you perpendicular actually holds for everything. And that's because we've got this absorption property of 0 in both the numerator as well as the denominator. Okay, so there are some rules for multiplication and addition. And now let's see how multiplication and addition might work together. Like in normal arithmetic, you've got some nice distributive rules. So do we have like something like that here? Okay, so now let's see if we've got distributive rules under this current arithmetic setup. So let's do this kind of via example. So let's do 2 plus 3 times, well, it doesn't really make sense to put a normal number or a non-infinite number over here because we know the distributive rules will hold. So let's maybe check this in terms of putting infinity here or the perpendicular number here. So let's start with infinity. So on the one hand, 2 plus 3 is 5, so that's 5 times infinity. But, we showed that 5 times infinity was equal to infinity, using our arithmetic rules on the last board. But on the other hand, if we look at 2 times infinity plus 2 times infinity, well, that's going to be infinity plus infinity. But infinity plus infinity was the perpendicular number. So in this case, it seems like the distributive rule does not hold. Well, let's see what happens if you put the perpendicular number here. So you have 2 plus 3 times perp. So that's going to be on the one hand 5 times perp, which is the perpendicular number. But on the other hand, if we were to distribute it, we would get 2 times the perpendicular plus 3 times it, which is the perpendicular number plus itself, which is the perpendicular number. So it seems to hold in this case. So let's maybe put an X right here and we'll put a check mark right here. So it seems to be working right there. Now, what happens if you've got like infinity or the perpendicular number inside of the parentheses? So let's maybe do 2 plus infinity times 3. So on the one hand, 2 plus infinity is equal to infinity. You multiply that by 3, you get infinity. Again, by our previous calculations. And then on the other hand, 2 times 3 plus infinity times 3 is equal to 6 plus infinity, which is infinity. So, well, it looks like this holds here as well. And, well, you can check that the perpendicular number is like so strong that it'll hold in this case as well. But what I mean by so strong is it like absorbs everything into itself in essence. Okay, so we've got 3 examples here. We've got 2 where the distributive rule holds, and we've got 1 where the distributive rule does not hold. So what we would like to do here is fuse them all together into some sort of equation that, is satisfied by all of them, that looks like the distributive rule, except it obviously isn't because the strict distributive rule does not hold. Okay, so let's see if we can do that. So here we have 2 plus 3 times the perpendicular number equals 2 times the perpendicular number plus 3 times the perpendicular number. I left a little gap right here because inside of that gap, I'm going to add the perturbation or the correction term to make this new distributive rule. And then similarly over here, we have 2 plus infinity times 3, plus this new term, which is yet to be determined, is 2 times 3 plus infinity times 3. And then the same thing up here. So let's see, up here we're gonna need 2 plus 3 times infinity, and then something equals 2 times infinity plus 3 times infinity. Okay, so now here to add the correction factor that'll work. So here we're gonna add infinity times 0, which is obviously the perpendicular number, making both sides turn into the perpendicular number. Here we're going to add 0 times the perpendicular number, which is also the perpendicular number, both sides of the perpendicular number. And then here we're going to add 3 times 0, which is 0. And I guess it's important to notice this one down here, adding 3 times 0, will extend down to, normal distributive rule type problems. 2 plus 3 times 5 plus 5 times 0 is definitely equal to 2 times 5 plus 3 times 5. So I possibly should have highlighted the importance of this thing that we're adding in to be something multiplied by 0 so that when we're working with finite numbers, it collapses to the normal distributive rule. Okay, so if we look at these 3 versions of our equation, I guess we've got 4 down there as well. What is our new distributive rule? Well, here it is. So we would have x plus y times z plus 0 times z is equal to xz plus yz. And in fact, every other weird thing that would happen in this wheel of rational numbers can be described by this new distributive rule. So that being said, if you're working with an abstract wheel, remember I said that this was an example of an algebraic structure called a wheel, you need a few more axioms. So let's maybe finish the video by looking at the axioms for an abstract wheel. Okay, so like I said, we're going to finish everything off with this definition of an algebraic structure called a wheel. So it's a set together with 3 operations. So we've got a commutative and associative addition and multiplication. So those are both binary operations. And I guess I should say that they come with their own identities. So 0 is the identity for addition, and then 1 is the identity for multiplication. I didn't write that here though. And then it's also got a unary operation, so that has a single input, and that is called this slash. So you can think about that as like taking the reciprocal, if you will. And well, here are the axioms that are satisfied. And notice I've got a lot of rules here that we didn't have with our, extended wheel rational number example, because a lot of those came for free based off of the arithmetic structure that we put on it. This is the only one that we had to include that was different than what we had before. Okay, so first of all, if you do slash twice on x, you get x. And this is like taking the reciprocal of the reciprocal and ending back where you started. And then if you do slash x and you multiply it into slash y, you get slash xy. So that's just this normal fraction arithmetic thing, if you want to think about it like that. Then you've got this like little tweaked distributive rule that we talked about before. And then you've got another like tweaked distributive rule over here when multiplying by slash y. So notice that the slash y distributes through, but then you have to pick up this plus 0 times y at the end. So that's again like a little correction to the normal distributive rule. We have 0 times 0 equals 0. So interestingly enough, this has to be an axiom here. With a ring, you can in fact prove that this is the case from the axioms of a ring, but you need this as an axiom for a wheel. And then another distributive rule for when you have multiplication by 0 inside of the parentheses. Here you've got a rule for slash x plus 0y. That's going to be slash x plus 0 times y. And then if you take 0 slash 0, so that's really like 0 times slash 0. So that's the element that we call the perpendicular element in our rational numbers. So if you add that to x, you get back to 0 times slash 0. Okay, so there you have it. You've got this new algebraic structure. And in fact, what you can do is you can take any commutative ring, well, commutative ring with 1, and you can form it into this structure called a wheel. Pretty similarly to the way that you can take any integral domain any integral domain and form it into its field of fractions. So I think that's pretty interesting. And that's a good place to stop.